Okay, so we are doing waves and wave properties, waves and waves properties, okay? And in addition to that, these are the guided notes that you should be taking notes on. Remember, you can just kind of click right here and you should be able to type right on top of them, okay? And this will be in your OneNote notebook, okay? If later on you want to go back and fill it in on the Google Notes, that's fine, okay? On the Google Slides, but we know Schoologie's down right now and you can't access it. All right, so we talked about waves a little bit last week, and you guys told me a lot of stuff that you already knew, which was great. So we talked about everything from the different parts of the wave, which we're not even going to talk about in this one, okay? The different parts of the wave. We talked about what type of waves, you guys. You guys told me about, some people said hair waves, like in your hair. Some people said waves like in the ocean. Some I heard people say sound waves. You guys gave me a lot of good stuff, okay? I'm sorry? Heat waves, yes, absolutely. Heat waves as well, okay? And we know that those are on the way, okay? All right, so waves and wave properties. So I want you to take a second, all right? And I want you to, this link right here is this video right here. So I want you to take a second and listen to this. If I can find where I lost it. Here we go. Okay. Imagine you're at the beach for a second. We'll talk about that in different class though. All right, so that is, so the question is, what is a wave? Okay, and we kind of talked about some of this last week. What do you notice about those beach waves? Like what stood out to you, or what also? The sound. The sound, okay, there was sound. Anything else? What about, what did you see? The light reflected on the water. Oh, very nice. Leo said he saw the light reflecting off of the water. I did see that as well. Okay. What did you see? Wind. Yep, I could see the trees were blowing in the wind. So I'm just gonna mute it, but we can. Well, what's the name of this thing that they use on the Netherlands to like have energy? Like windmills? Yeah. Windmills, yeah, yep. So what about the direction of the waves? Like when you look at this, because this was interesting, because what somebody said they saw in third block, I saw something different. So when you're looking at the direction of the waves, which way do you think it's moving? This way. Which way? Forward. Forward. Okay, so Esther says she thinks the wave is moving forward. So moving like this direction, Esther, like my mouse, like this? The other way. The other way? Like this? No, forward. It's coming towards me. Coming towards, oh, it's coming towards you. Okay. So that's one of the interesting things that I noticed. Okay. So, okay. What I noticed last block was somebody said, hey, Miss Peyton, they said when they looked at it, they thought the waves were moving this direction. So kind of like a left to right direction. So kind of like, let me draw here. They said the waves were moving like this, okay? Actually, no, I said that's the way I saw the waves moving. They said they saw the waves moving like this. So they're thinking about the water going like this, okay? And I saw the water moving more this way, okay? And technically, who's right? That's what I think. Natalie, who do you think is right? Was the waves moving? Do you think they were moving up and down, or do you think they were moving left or right? What do you think, Natalie?
Left to right.
Left to right, okay. Antoine, what do you think? Left to right or up and down? Left to right, okay. So when we talked about it and we found out later on, we actually kind of were both right, okay? So in my mind, the waves were moving this way, but the particles in the waves were moving this way. And we're going to talk about that. Remember what Dr. Hagelin talked about, the upside down T for transverse waves? So that's what we're going to touch on today, okay? All right. So now, okay. All right, so now let's go to the next slide. All right, and this is probably when our notes are going to start. Okay. All right, so a wave, this is where your notes come in. So remember, this is where we are in your notes. Okay. Right here, a wave is, okay, I'm just going to zoom this in a little bit. A wave is, and here's what I have. It is a disturbance that carries energy from place to place. And this is what we are typing in our notebook. Typing in our notebook. Okay. This is the first thing we're filling in our notes. All right, so a wave is a disturbance that carries energy, specifically, okay, carries energy from place to place, okay? And they're often caused by vibrations, okay? So think about vibrations, things hitting each other, okay? That's what we're going to talk about, okay? All right, so it carries energy from place to place, carries energy from place to place. All right, moving on. Yes. All right. A wave does not carry matter, okay, with it. It just moves the matter as it goes through it. So, in other words, I'll let you write that down and then I'll explain what that means. Okay, so what I mean by a wave does not carry matter with it, it just moves the matter as it goes through it. In other words, the matter or the stuff that's being moved is just moving, but it's moving in place. It's not being relocated. So for example, in a little bit, we're going to talk about, in a second, we're going to talk about, like, for example, an earthquake, okay? An earthquake, there's energy that moves through the ground. It doesn't pick up this road and put the road somewhere else. It's just that the road is shifting because of the energy moving through it. So it may break it up. It may like move a little bit left to right, but it's almost just like vibrating in place. And sometimes the vibrations will cause it to shift, but it's not being relocated somewhere else. Okay. All right. So that's what we mean. But the energy does move through the wave. The energy moves through the wave, but not the matter. Okay. We're gonna do that's what this whole presentation on. We're gonna talk about that. Okay. All right. So here is, yes. Go back. I am. Okay. All right. So here is a stadium wave, okay? So if you've never seen a stadium wave before, sometimes if you go to like a football game or a baseball game or a soccer game, other football game, you'll see people do the wave where everyone's in their seats. Nobody moves seats, but they all stand up, they pull their hands up to the top, and then they pull them back down. And that's what happens. So let's look at what a stadium wave looks like. Okay. Not yet. I'll tell you when. Okay, so let's look at a stadium wave. Okay, a stadium wave. All right, here is an example of a stadium wave. All right, and let me see if I can, I know sometimes it's lagged because of Zoom, so let's see if you can see what's happening, okay? I'm gonna try it. Let me see if I can play it in super slow speed. Let's play it in half speed. Let's see if that works. Here we go. So you can see, kind of, I'll put the link in, but you can see people standing up, they're throwing their hands up in the air, and then they bring their hands back down, but their people are doing it as they go around the field, okay? So in this case, the people are the matter, they're not moving, but the energy of them lifting their arms is moving through. You can see it good right here. So you can see it's just kind of going down, going down. That one's a good one. So you can see it. It simulates a vibration, exactly, okay? So this is a stadium wave, okay? All right, so in a stadium wave, okay, before and after the wave, the people are still in the same place. So now, back to your notes, okay? Matter, which in this case is the people, stay in the same place, okay? But the energy moved, okay? And if you really think about it, it's these people's kinetic energy, right? They're sitting still, potential energy. Then kinetic energy, they stand up, they move their arms up, they bring their arms back down, they go back into potential energy, and it moves around the stadium, okay? So you should be on your notes right now. You should be filling in right here, okay? Stadium wave. You can see these people standing up, they're moving their waves. No matter the people stay in the same place, but the energy moved, okay? Right here, matter or people stay in the same place. Energy moved.
I am so sorry. Is that you? Yeah.
All right, so here we go. Now let's talk about, think about an ocean wave, okay? Think of an ocean wave. The waves are constantly happening, but it says we never run out of water, but what I really want to say is like the water doesn't like disappear. You don't get more water. It's the same amount all the time, okay? It stays in the same place. It's just that the water is moving kind of up and down, okay? So the matter or the water stayed in the same place, but the energy that's going through the water moves, how you said, left to right, okay? Exactly. So when there's a tide, okay. Oh, when you're saying, oh, that has to do with the moon. That's getting into a whole nother science. But it's not going away. It's just a high tide and a low tide. I know what you're saying. So the water is moving in, if this makes sense, the water is moving in place. Okay, so it's kind of like, it's like, yes, exactly. But the water is not necessarily getting displaced or moving to a different location. I'll show you, I'm going to show you some more examples. I'm going to show you like
in that wave right there, like at the top, that water,
it's going to go up and it's going to come back down.
But it's not moving. The
energy is moving through that water.
Okay.
It's, think of, let me see how to say this. Let me show you, I'm going to show you on particles when we talk about transverse waves, okay? All right, everybody got this down? Can I go to the next slide? Okay. All right, so here are the two different types of waves. You have a mechanical wave. Mechanical waves need matter or medium, okay, to transfer energy. And then you have electromagnetic waves that do not need matter or a medium to transfer energy, okay? So I was pretty impressed with myself. Last period, I was like, how am I supposed to remember which one needs matter? And I was like, okay, mechanical needs matter. I'm sorry? You're right here on your notes. See, we just finished ocean waves, and then it says two types of waves.
What was the ocean wave again?
The ocean wave is going to be a mechanical, and I'm going to show you why in just a second, okay? Oops. Yes, so it says mechanicals need matter. Electromagnetics do not. So this is how I'm going to remember that mechanicals need matter. I looked at it and I said, oh, this says mechanicals need matter. And to me, that looks like M&Ms, M&Ms.
Does it need medium?
Look at what this says. It needs matter, okay? And matter is medium. It's the same thing, okay? So a medium is matter, okay? Electromagnetic waves do not need matter or a medium to travel through or to transfer energy, okay? So again, this is how I remember which one between electromagnetic and mechanical, which one needs matter. I think about M&Ms. M&M, mechanicals need matter, okay? Mechanical needs matter. M&M. Yep, M&M. I used to love M&Ms when I was little. I've graduated to Snicker bars and Reese's cups now.
Bar?
Yeah, I love Snicker bars.
You said, nickel? Nickel bar?
Snicker,
Oh.
okay? All right, so we got mechanical waves need matter to transfer the energy, and electromagnetic waves do not need matter to transfer energy, okay? Now, I want to be very clear. Let's talk about mediums just for a second, okay? Because sometimes we think there isn't a medium, but there is, but maybe we just can't see it, okay? So here is a medium. A medium, okay, a medium is the, a medium is the substance through which a wave can travel, okay? Now, it's interesting because, so medium and matter are basically the same thing, but it's interesting because I want you to know that it's easy for us to see a solid and a liquid and water, that's obvious, okay? But gases and air are also mediums, okay? I cannot see air, but it doesn't mean that it's not there, okay? Because if you go, yes, it is right. So in other words, you can have no medium. That means there's no air. Where would you have no air, no gases? Space, right? So you have some waves that can travel through space without a medium, or even if they look like if they're traveling through air, they're not actually traveling. They don't need the air to travel through, okay, or the energy. Yes.
Are the gases coming from the
We're just saying, oh, this right here, that's for gas. But we can't actually see it. It's water in gas form, okay? All right, so you need to remember that a medium is matter, okay? And who needs a matter to travel through? What type of wave? Electromagnetic or mechanical? Which one needs a medium? Mechanical, M&M, right? Mechanical. M&Ms, mechanicals need matter, or mechanicals need a medium, however you want to say it, okay? I just like the plain ones.
And then the caramel ones?
Never had the caramel ones. Don't judge me, we'll talk about it later. We'll talk about it later. All right.
Anything peanut sucks.
They suck booty.
All right, here are examples of mechanical waves. You got sound waves, ocean waves, earthquakes, and then wave of people at a sporting event. You don't have to write all of these down, but you should be writing down some of your examples in your box on your notes. Yes? Okay. All right, so you got sound waves, ocean waves, and earthquakes. So remember we were talking about the earthquakes earlier, and we were talking about, so think about it. What if earthquakes could just travel through nothingness? I mean, what makes it an earthquake? It wouldn't be an earthquake anymore. It'd be a quake. A quake of what? I don't know. It's not going to hurt anything because it's not traveling through anything. Okay.
When you mean traveling to the earth.
Yeah, that's what. That's exactly what an earthquake is. Traveling through the earth. Okay. All right. And then I'm really excited. In like a couple of days, we're gonna really focus in on sound. Oops, sorry. I'm going back. In a couple of days, we're going to focus in on sound waves. This is one of my favorite things to talk about. I think they're so cool. Okay. This is for mechanical, yes. Okay. Sound waves, ocean waves, earthquakes. Just give me a couple of examples, okay? All right. And then, here we go. So then, next we have examples of electromagnetic waves. These are the ones that do not need a medium. Do not need a medium, okay? All right, do not need a medium. So you have light waves, which Anaya actually mentioned earlier. Light waves don't need a medium. Radio waves, not to be confused with sound waves. Microwaves, X-rays, those do not need mediums in order to for their energy to travel through.
Is a rainbow a radio wave?
That microwave
It's not.
how they used to.
It's not.
Oh God.
Those are light rays.
The microwave might price 3 times for them to get like, hot.
All right,
6
so
minutes.
next
3 times.
our waves are caused by vibrations. All right, so I'm gonna call on 5 people. All right, if waves, so listen very carefully, if waves are caused by vibrations, if waves are caused by vibrations, which state of matter will waves have the easiest time traveling through? So in other words, which one is going to vibrate the easiest? Is it going to be a solid, a liquid, or a gas? What do you think?
Say that again?
So my question is, if waves are caused by vibrations, okay? So you have to, in order for you to have a vibration, you have to have, in order for you to have a wave, you have to have a vibration. In what state of matter is it most likely for you to have vibrations? Okay. Eric says gas. Kevin, what do you think? Solid, liquid, or gas? What do you think, Kevin?
What was the question again?
The question is, if waves are caused by vibrations, okay? If waves are caused by vibrations, which one of these is most likely to have vibrations, basically? Because that's what we need in order for a wave to happen. Solid, liquid, or
Liquid.
gas? All right, Kevin says liquid.
I'm gonna say solid.
Joel says solid. Okay, we got somebody for everything. We got a couple of people with gas. Well, sorry, that didn't sound right.
I said solid.
Naya says solid. What do you say, Garrett?
Yeah.
Gas. What do you think, Sarah? Solid, liquid, or gas?
Gas.
Gas.
Thank you, Sarah.
Carla, what do you think? Solid, liquid, or gas? Carla said.
What was the question?
Carmela says liquid. So the question is, if you have to have vibrations in order for a wave to exist, okay, you have to have vibrations, okay? Which one of these states of matter, solid, liquid, or gas, do you think a wave would travel easily through, or would it even be created in? A solid, a liquid, or gas, which vibrates the easiest?
I think a liquid.
Okay, so we had a little bit of everything. And let's see who was right. Well, let me ask you this. Let's look at these pictures before I tell you the answer, okay? If you put your hand on one of these, which one do you think you would feel the vibration in?
Liquid?
Okay, liquid, Leo?
Yeah, but that's
So
space
solid.
between.
I was right.
No, but that doesn't mean it's the easiest to travel through.
It is a solid.
Boo.
All right. Okay.
Oh, I'm smart.
You are smart, Joa. All right, let me tell you the totally Let me tell you the totally inappropriate conversation we had in third block about this, okay? So, you ready? All right.
Yes.
Inappropriate, and I probably shouldn't be recording this, but if it helps you understand, I will sacrifice the appropriateness for this, okay? All right, let's do it. Here we go. Someone brought up farting, okay? All right, I'm just saying, wasn't me. It was not me. It was not me, but I said, so once they brought that up and we were talking about vibrations, okay, I said, when is the last time, okay, when's the last time you stood up, you were standing up, you weren't touching anything, and you let one rip and something in the room vibrated? I'm just saying, when is the last time you stood up, okay? You stood up and you farted. Yes, fart. What's another word for fart? Let one rip, okay? And something in the room, like, what if Eric was standing right here and he farted and all these stands just fell over? Oh my gosh, right? What if all this stuff, all these little shields behind him just fell? Okay. Yes, all right. But okay, what if you were sitting in a chair?
I accidentally did that
Was it an accident, Esther? Was it an accident? Maybe it wasn't. Maybe it wasn't.
And the
But-
ones behind me didn't look at me. I said, what are you looking at?
Oh my goodness. Not only do you get the vibration, like you can feel it if you're sitting in a chair, right? But you also get some sound waves a lot of times. That's probably what happened with Esther. She probably had some sound waves.
The only them could hear.
That's what I'm saying. That's a sound wave, right? Yeah, that's what I mean. We're hopeful. But anyway, so the molecules are so close together when it's things that are touching, like you sitting on a chair, okay, then that's more likely to cause a vibration. So
Well, next time I know where to.
now you know how to relate.
Them
Your fart
silent
waves.
ones be definitely going.
Okay, let's keep going. All right, so yes. So Joel, yes, you're very smart, along with some other people. Not that everyone isn't smart, but Joel did guess it. He said solid. So they're all close together.
I didn't guess it.
Yeah, Joel did not guess it. He knew exactly what he was
I didn't
saying.
guess. I said solid.
Oh, you did.
I actually did.
Okay, I'm sorry. But yes, if you look at these pictures, these guys are already touching. So these vibrations you're gonna feel. Like a gas is so far apart, like how's it gonna vibrate? These aren't even touching, okay? These aren't even touching.
Thank you.
All right, so moving on, here are the two different wave types.
In space.
Now, here are the two different wave types. The first one is transverse, focus, transverse, okay? So remember, we talked about these last week. These are the ones in where you make right angles, or it is, what was that word that started with a P? Started with a P. What was it last week?
Perpendicular.
Excellent, perpendicular, all right? So remember, if it's perpendicular, you get this right angle right here, okay? And I'm going to show you that slinky video that we watched last week again, but you get this right angle, okay? It's perpendicular. So what that means is, just like we were talking with the ocean waves, okay? Just like we were talking with the ocean waves, what happens is you tend to have the wave moving. Let's do a different color here. Okay, you have the wave moving in one direction, okay? Let's say left to right, something like that. But in actuality, the matter, okay, so the energy is moving left to right, but the particles are actually moving up and down, okay? They're actually moving up and down, okay? So that's how you get that right angle right here, or it's perpendicular, okay? So let's look at that video again. I'm gonna play it in slow motion. We're just gonna look at a small clip of it, okay? Let's look at that video. Okay, here it is, transverse. Let me clear my drawings here. So I want you to look very closely. Look at his hand. His hand is going, or hers, up and down. Okay, remember we talked about this? So the direction of the vibration is going up and down, but the actual wave is going left to right, or specifically, it looks like it's going to the left, okay? Or maybe it's going to the right, right? So here, again, you have that nice 90-degree angle right here, okay? 90-degree angle, all right? 90-degree angle, and that's for a transverse wave. And if you remember, again, when Dr. Hagelin talked to us about it, again, he said, when he thinks about transverse waves, how he remembers that this one is the 90-degree angle, he takes that T, okay? He takes the T from transverse, he flips it upside down. Here's his T upside down. And then he said he uses that to make his right angle, okay? That's how he told us. All right, so the wave is moving right to left, but the matter will move up and down, okay? But the matter will move up and down, okay? All right, so here's an example, and here's the picture that I really like for you guys to see. So this is kind of what you were asking me about, Leo, okay? So let's look at this one. All right, here is the initial position of the particles. So this is where the particles were before we start moving them, okay? And then let's just say that these particles here, okay, let's just say that those particles right there are the particles, let's just say it's on this string. It's the same particles that's on this string, okay? So as soon as this guy starts moving his hand up and down, okay? The particles are gonna do the same thing. These particles are gonna move, like right now they're moving down, but eventually it's gonna be moving up. But this particle is gonna go up and down, up and down, up and down, okay? Same thing with this particle. This is where it starts. It's gonna move up and then it's gonna move down as he's flipping that rope, okay? Up and down, up and down. But the actual wave that you see is going this way, left to right, because this is going to loop like this, okay? It's looping this way. And remember that loop is going to continue. So it's gonna keep looking like this, right? It's gonna keep looking like that. So the wave is moving left to right, but these particles, like this particle right here, it's gonna stay right here. It's just eventually it's gonna be up here and then it'll be back down here again, and then it'll be up here and then it'll be back down here again, okay? Particles are moving up and down. The wave is moving left to right, okay? Do we have this down in our notes? Let me show you where you should be in your notes. Okay, you should have all of this filled in. We should be on the second page. You should be right here, okay? So waves in which the medium moves at a right angle to the direction of the wave.
Angles or angles?
It doesn't matter.
Okay.
Right angles, right angle, okay?
Maybe I have to put solid in the box.
For this box, yes, you should put solid and then you should say Y. Okay, and it's just that they're close together. Look how tight these particles are close to each other, okay? So that's what you should have in this box. Yes, they're close together, okay?
With a comma, solid.
It's totally up to you.
comma, They are close together.
It's up to you. These are your notes. All right, so that's a transverse wave. And then does anybody remember what the other wave was? It started with an L. Longitudinal. All right, here we go. Oh, here's some examples of transverse waves. Okay, light waves, radio waves, guitar strings. When you flick it.
Is that a, oh my, I have never seen this.
A guitar?
No. The strings are like
Oh yeah, maybe they're broken. I don't know. Okay, stadium waves and ripples in water. Okay, so these are examples of transverse waves. Okay, all right. Here are the parts of the transverse wave. We've talked about this before. We actually talked about more than this. We also talked about what it was called when you went from crest to crest and trough to trough, but we'll talk about that next class. Okay. So the high point is called the crest, and the low point of the wave is called the trough. So you have a crest here, but you also have one right here, and there's the start of one right here, and the start of one right here. And then this is a trough, and then this is a trough, and then this is a trough. So the lowest point is called the trough, okay? So it's kind of like hills and valleys, basically.
You say trough instead of true?
Trough.
Trough.
Yes, so the GH makes an F sound, trough.
Trough.
Yes, okay. All right, so those are the parts of the transverse wave. Now we're at the longitudinal waves, okay? And these, they move in the same direction, okay? So if the wave is moving left to right, so is the matter, okay? I'm gonna show you guys a really cool example in a second that I never even thought about. I was like, oh, this is such a cool example, okay? I'll show you one. We do have the video that Dr. Heglin showed us that looks like this. It was also with a slinky, but this one was longitudinal. Let's see this one. All right.
It's taken.
Yes.
You know that somebody from our school.
Just remember I'm recording. Yes,
Did you know somebody from our school is doing something?
I did not.
She was our news anchor.
Cool. All right, so on these, you can see the direction of the wave. Please focus. The direction of the wave is going in the same direction as the direction of the vibration, okay? And you can see these like really kind of thick parts that are going through. So like if I pause it right here, you can see like this part is really spaced out. This part is super scrunched up together. And then this part is spaced out again. And there's names for those. And that's what we're going to write down in just a second. Okay. But again, there's no up and down motion. Even if you look at his or her hand, is going in the same direction as the wave. Okay. These are called longitudinal waves. Okay. All right. So longitudinal waves, here's some examples: sound, pressure after an explosion. Is there a blank? Okay. All right, so here are the vibration of the particles are going in the same direction as the wave. Okay, same direction as the wave. Okay, same direction as the wave. Okay.
What's pressure after an explosion?
We'll talk about it. It's just the energy that moves out through an explosion moves out the same way that everything is moving. Okay. All right, so now let's see where we are. We should have almost everything filled in. Let's see. All right, we're down to talking about those really tight parts that are squeezed in and those really loose parts, okay? So let's talk about that really quickly. Oops, all right. So this is a spring, all right? And we're gonna talk about how the parts that are close together or the parts that are compressed are called compressions. And the parts that are spaced out are called rarefactions, not fractions. I always wanna say fraction, but it's rarefaction, okay?
O Ítalo ele tá ausente aqui no LoL. Não sei se ele tá online.
He unmuted his mic.
Yeah. Joel, you are unmuted. All right, here we go. So rarefactions and compressions. Compression, where the particles are close together. Okay. And rarefactions, where the particles are spread apart. Okay, so get this down. All right, so again, compression are where the particles are close together or they are compressed. Remember, compressed means close together. Rarefactions are where the particles are spread apart, okay? All right, so this is just another example of where you can see compressions and rarefactions, okay? All right, so that is the note. So let me tell you what activity you guys have, okay? You have an activity where we're gonna figure out if the waves are longitudinal or if they are transverse, okay? And I know your Schoology is not working right now, so let me just show you this one example and how you're gonna do it, and then you're gonna do it for homework before class next time, okay? All right, so I'm going to, there is in your folder, okay, it's called Types of waves activity is down here. And I know that you cannot get into Schoology right now, but when you open it, it looks like this. What kind of wave is this? What kind of wave is this? Okay. It will not take you long to do this at all. Okay. So you can have, I'm sorry? This is the only homework. So there are, I'm not even worried about you finding your own example. Okay. So there's 1, 2, 3, 4, 5, 6, 7, 8 of these. I'm going to do this first one with you. Okay. So what you would do is you will put your mouse over it and you will see a YouTube video pop up for all of these. Like we already did the stadium wave technically. I'm going to do the traffic wave in just a second, but you click here and here are the different little small videos. The longest might be 2 minutes. You don't even have to watch the whole thing. Look, we've already watched the 2 slinky ones. Okay. Here's an earthquake one. They're really short. I think all the videos together is still less than 10 minutes. Okay. You don't even have to watch the whole video just until you get an idea of whether it is transverse or longitudinal. Now, remember, we talked about transverse, T upside down. It makes a 90-degree angle. Okay, so that means that this is 90-degree angle right here. Okay, so that just means that the matter is going up and down while the wave is actually going left to right or something like that. Okay, versus a longitudinal wave where they are both moving in the same direction. Okay, both of them are moving in the same direction. So for example, for the traffic one, okay, for the traffic one, let's look at that. Here is an example of the traffic one. We can just look at this lane over here. Okay. So we're trying to figure out, is this a longitudinal wave or a transverse wave? Okay, we're looking at this.
This looks crazy.
Okay, this is what traffic looks like. So what do you think?
Yeah, but like it's from
Long.
the whole day.
The one that they go together.
From the whole day, but slow down.
Mm-hmm. Or sped up, actually. Very nice, Joel. I agree with Joel. So Joel said he thinks this is a longitudinal wave. I agree with him. So like, look, if I look right here, just even if I snip it right here, all these cars are kind of bunched up together, okay? But then right here, they're pretty spaced out apart, okay? And even if I go back some, hit play, look how they start to bunch up, then they space back out, then they bunch up again, space out, okay? You can see how they're spaced out again. Bunched up right here, spaced out. So I agree with Joel. Okay, so on here, I would say that they are longitudinal. Okay, and this is what you'll do. And then I would say, why do you think this? And you can say whatever you want. You can say some parts are spaced out, some parts are close together. Or you could also say, for example, if this had been transverse, okay, since the wave is moving in this direction, okay, left to right, if this had been transverse, that means the cars would have to be moving up and down, literally coming off of the road into the air and then coming back down onto the road. That is definitely not what's happening here. So that's not a transverse wave, okay? All right, so that is, I know that Schoology is down, but that is what you guys will be doing.
When I first like
For-
Long.
Yeah.
Long.
Longitudinal?
Long.
You can just say long wave, okay?
Longitudinal.
Uh-huh.
Because it's moving, because it's spacing and then it's.
Yes,
triangle.
exactly. It looks just like, kind of like this. It have parts, and it doesn't have to be necessarily an order to it. Like it doesn't have to be, for example, like, the spacing doesn't have to be exact. So like this part right here could have been more over. It doesn't have to be like, as long as you see spacing and then it gets close and then it gets spaced again and close, doesn't have to be at an interval, okay? All right, that is all I got for you guys.